Look at a map, and the blue dominates. Earth's oceans stretch across 70% of the planet's surface, forming a massive, interconnected envelope of liquid. But if we isolate just a single cubic mile of that water, we find something remarkably heavy hidden inside. This specific block holds roughly 120 million tons of solid, dissolved salt. When scaled to the entire volume of the sea, the ocean reveals its true nature. It is a densely packed global storage basin for solid minerals. This brings up a physical contradiction. The primary systems feeding this basin are rainfall and runoff. We universally classify both of those sources as fresh water. We drink from them and we irrigate our crops because they are entirely salt-free. So if billions of gallons of supposedly pristine fresh water are pouring into the ocean every single day, why does the basin remain intensely salty? To find the answer, we have to look past the surface. Rivers and oceans operate together as an interconnected global machine, a terrestrial delivery system feeding directly into an inescapable trap. The delivery mechanism starts miles above our heads, with a single drop of rain falling through the atmosphere. As that water falls, it acts like a sponge, absorbing carbon dioxide directly from the air. This chemical reaction turns the falling rain slightly acidic by the time it reaches the ground. When this mildly acidic water washes over the land, it acts as a slow solvent. It erodes the rock surface, picking up trace amounts of salts and dissolved minerals. This model shows why rivers don't taste salty. The water does contain those minerals, but the continuous high-velocity current ensures they are swept away before they can ever settle or accumulate. Every river on Earth is effectively a high-speed planetary conveyor belt, quietly smuggling millions of tons of terrestrial minerals off the continents. The momentum of that conveyor belt only drops when the river spills into the ocean basin. The continuous flow stops, and the minerals begin to pool. Once stagnant, a biological filter separates minerals into two paths. Marine life pulls calcium out to build shells and complex structures. This strips away usable nutrients, leaving behind salt. With no biological use, the salt remains, turning the basin into an undrinkable brine. While salt accumulates from the surface, a second engine is at work in the pitch-black cracks of the deep-sea floor. Here, ocean water seeps deep into the Earth's crust until it makes direct contact with superheated magma from the planet's core. This extreme heat triggers a violent chemical exchange. The water sheds its oxygen and magnesium while simultaneously ripping metals like iron, zinc, and copper straight from the surrounding rock. Under immense pressure, these dissolved metallic salts are blasted back up into the ocean through towering hydrothermal vents. The ocean's salinity is the result of this two-front geological assault, a slow, invisible weathering falling from the sky and violent chemistry erupting from below. Viewed as a whole, the ocean system operates as a massive closed loop for liquids, but a total dead end for solid matter. The sun heats the surface water until it turns to vapor, lifting back into the atmosphere to restart the rain cycle. But there is a physical limitation to this cycle. Only the water evaporates. The heavy salts and metals are left behind, physically unable to leave the basin. This makes the ocean Earth's ultimate trap, a one-way sink where billions of years of terrestrial erosion and tectonic activity pile up with absolutely no exit. This chart reveals the makeup of that trapped accumulation. Of all the minerals in the sea, sodium and chloride dominate exactly 85% of the mixture. Compared to the total ocean volume, those minerals represent just a 3.5% slice of the water we know. Despite its saltiness, this specific brine is not a wasteland. It is the precisely balanced foundational habitat for all marine plants and animals. Because the ocean is a one-way sink, it has no way to flush out the substances we introduce. Any synthetic pollutants we allow into our rivers will eventually be trapped alongside the salt, making the protection of our terrestrial runoff the only way to preserve this ancient, delicate balance.